students, in this lecture we will talk about diode lasers. Now, unlike normal lasers, in diode lasers you don't require any external mirror. So no external mirror for cavity formation is required. The cleaved planes at the two ends of the waveguide essentially provide the required reflection for cavity. So this is done by the cleaved planes at the two ends of the waveguide. They provide the necessary reflection to form the cavity. Necessary reflection to form the cavity. Now, the reflectance at the semiconductor air interface. So, reflectance at semiconductor air interface is given as R is equal to nR2 minus nR1 divided by nR2 plus nR1 whole square, where nR2 is the refractive index of the semiconductor, and its value is typically 3.6, whereas nR1 is the refractive index of the air, and it's typically 1. So the value of R comes around equal to 0.32. Now these cleavage planes of a crystal are perpendicular to the direction along which the bond strength is the smallest. For example, so in case of gallium arsenide and other 3, 4, 3, 5 compounds, these cleaved planes are 1, 1, 0 planes. Whereas in a typical junction laser, the junction coincides with the 1, 0, 0 plane, which is the direction of growth. Junction laser 1, 0, 0 is the direction of growth. And mirrors are formed by cleaving the opposite 1, 0, 0 plane perpendicular to the growing direction. These mirrors are formed by the 1, 1, 0 planes in the opposite direction. Now, you need to have two different mirrors. This is where the light will reflect back and forth, and there will be a population inversion. So that's how the lasing action will take place. So in the case of diode lasers, these are provided by the cleaved planes of the material, or the cleavage planes of the material that is taken. So these are provided by the these, whereas in normal laser you have to mirror, so here mirrors are not required. Now with the active region of the junction laser, the gain will eventually exceed the losses with an enhancement in the rate of stimulated emission. So no, outside the, so there will be an active region. So if we consider the gain plot, so there will be one active region denoted by this thickness T, and inside the active region, so we are talking about the gain. Inside the active region there will be a loss, there will be a gain, whereas outside the active region there will be loss. This is the gain versus thickness, I should say, of a diode laser. So a diode laser basically looks like this. You have a ohmic contact on the surface, and so this is the ohmic contact. We have P-gen, sorry. We have a P junction and an N junction. This is the direction of the current. And this is the small t that we talked about here, and this is the active region. This is basically the active region where we are getting an enhancement of grain. This is this region. Now, population inversion or gain occurs over an active thickness T, as I have told, which is a homojunction laser, and is approximately equal to the diffusion length of the injected carriers. So this is what this D is approximately equal to the diffusion length of injected carriers. However, there has to be a frequency where the optical mode extends, so that distance is little bit different. So we take that distance more than the D value. So this is where the optical mode is active, and this is, we take it as dm. So dm is slightly more than d. Now the confinement in a homojunction laser is extremely poor, and the active region is defined by the stimulated emission and resulting gain in the region. Now, as the rate of stimulated emission increases in the active region, so what is happening, due to these cleaved planes, the light is getting reflected back and forth between the two planes, so the stimulated emission is increasing. So let's write it here. Stimulated emission, it is increasing. Also the population inversion, that means more number of atoms at the higher state and then the lower state, this is also increasing, and this is in fact causing the gain. The gain is being increased in the active region. Now, as the rate of the stimulated emission increases in the active region, the round trip gain in the cavity overcomes losses and the lasing commences. So the injection current at which this occurs is called threshold current. So there has to be some injection current where the stimulated emission is increases and it overcomes the losses and we get lasing action. Lasing takes place, so this takes place at a threshold current. So this threshold current can be represented graphically. So we have a light output. And we have a current here. The plot is 2. So the plot looks like this. So this region is your spontaneous emission. This region. This increase in output is due to stimulated emission. And if we draw a tangent, this is the threshold current. This is a threshold current. Now, the nature of the spectral output it also changes as incoherent spontaneous emission below the threshold is eventually replaced by dominant laser mode threshold. So basically, we have 3 types of output intensity versus frequency. So first is below. So the first one is below threshold current. So plot is like this. This is output intensity, and this is frequency mu. So this is below threshold. At the threshold, the plot changes to shape like this. So here what is happening, the laser mode is emerging. That means it has started to take place, lasering action is started to take place. And these modes are basically seen in LEDs due to the boundary conditions imposed by the structure. So this is where the lasering action has started to take place. So this is where this change in the plot, and the last stage where beyond threshold means total lasering action has been attained. and there are no losses involved. It simply will show a peak like this. So this is where the lasing action is dominant over the losses. So these are the three types of output intensity with frequency for a laser diode.